morning, students. I'm Chaitanya, Assistant Professor in Mathematics, Department of Freshman Engineering, Institute of Aeronautical Engineering, located at Dundigal, Hyderabad. In the last class, we started a course in our curriculum titled Probabilistic Modeling and Dimensionality Reduction Mathematics. And I have given an introduction lecture on dimensionality reduction in the last class. Also, we have discussed in brief about the course structure of the subject probabilistic modeling and dimensionality reduction. Now today we are going to discuss the next concept, the principal component analysis. That means we are entering the mathematical perception of dimensionality reduction. Okay, so we are going to discuss the principal component analysis, its meaning and its role in the reduction of dimensionality of a large database sets. Okay, so this is the title of our chapter, probability modeling and statistical data sets, and we are going to discuss the principal component analysis. Principal component analysis is also known as PCA in short. So what is the principal component analysis? How it is related to dimensionality reduction? The most common approach to dimensionality reduction is called principal component analysis. There are several approaches in reducing the dimensions of the large data sets, okay, and reducing into smaller data sets. There are several approaches, and one of the most popular approaches, the PCA, principal component analysis. PCA generally tries to find the lower dimensional surface to be projected the high dimensional data. That means it is nothing but a mathematical procedure by using which we'll try to project a high dimensional data into a low dimensional space. That means we'll try to reduce 10 features into 3 features possible. Like for that, we'll apply some mathematical process that is known as principal component analysis. Let us look into the things in detail. PCA works by considering the variance of each attribute because the high attribute shows the good split between the classes and hence it reduces the dimension. So PCA, the mechanism of PCA basically depends on the variance of each feature on each attribute. That means we consider every column of the data. If we arrange the data sets in a matrix, every column is known as a feature that we have discussed in the last class. So x1 is a feature, x2 is a feature, and so on, xn is a feature. Let us suppose. Then we'll calculate the variance of each column vector as well as we'll calculate the covariances among those column vectors. And with that we'll form a matrix. And with the help of that matrix, we'll try to reduce the high dimensional attribute into a low dimensional attribute. That is called PCA, principal component analysis. And the applications, the real world applications of PCA are image processing, movie recommendation system, optimizing the power allocation in various communication channels. Image processing, we can process an unclear image into a clear one by using principal component analysis. Also, if the image occupies a large set of data in the system, we can compress the image without disturbing the essence or the clarity. We can compress it and we can save it in a less memory of bytes. So for that, we'll take the help of PCA. So image processing to increase the clarity, to remove the noise, and also to save the storage space, we need dimensionality reduction, which is done by PCA. And also movie recommendation. If you see Netflix, Amazon, from so many OTTs are available today. In those OTTs, according to your taste, so pictures will be filtered and they will be coined in front of you. Okay, this is because of the PCA, principal component analysis, and machine learning and artificial intelligence, the coherence of these things, dimensionality reduction, machine learning, and the artificial intelligence. All these things go coherent to do these things. Okay, and optimizing the power allocation in various communications. When you're using various communication channels simultaneously at a time to optimize the power, also we need artificial intelligence, which takes the help of machine algorithms, which are dependent on dimensionality reduction, and the process behind it is principal component analysis. Okay, and so it is a feature extraction technique. So it contains the important variables and drops the less simple. Dimensionality reduction is nothing but if we feel that a database is very large, we'll drop out the unnecessary variables. We'll keep the only necessary variables out of thousands and lakhs of thousands of unnecessary variable sets. You'll just cut off the unnecessary ones and you'll keep the necessary ones in such a way that the essence of the information is not disturbed without any loss of information. We can uh, preserve the content. Okay, right. Now, the PCA algorithm is majorly based on two important mathematical concepts, namely variance and covariance of variables, random variables or column vectors, and the eigenvalues and eigenvectors of a matrix, of a square matrix. So these mathematical concepts will play a very important role in the principal component analysis, and hence reducing the dimensionality of a large sets of data into small sets of data. Principal component analysis is a dimensionality reduction method. Let us look into the meaning. What is principal component analysis? Principal component analysis is a dimensionality reduction method that is often used to reduce the dimensionality of large data sets by transforming a large set of variables into a small set of variables. Still contains most of the information in the large. Just we have discussed a few minutes ago, the principal component analysis helps in dimensionality reduction. Nothing but reducing the dimensionality of large data sets into small data sets by removing some variables and with a reasonable number of variables in such a way that the information is not lost. The information is preserved. The essence is preserved. Okay, that is the motive of dimensionality reduction. And reducing the number of variables of data set naturally comes at the expense of accuracy. You may ask, sir, if we reduce the number of variables, suppose if 1,000 number of features are reduced to hundreds, there is a possibility of losing the accuracy, losing the information. How could we save the accuracy to the maximum level, maximum extent? That is the question. But in the dimensional reduction, we'll take all the cautious steps to trade a little accuracy for the sake of simplicity. That means, of course, we may lose out of 100% of quality, picture quality. We may lose at most 1% or 0.5%. But we could preserve at least 99% of the information is preserved. We take all the precautions with all mathematical measurement. That is called principal component analysis. Because the smaller data sets are easier to explore and visualize and make analyze the data much easier and faster for machine learning algorithms without extraneous variance. See, this is an important point. Why we need to reduce a big, huge, large data sets into smaller data sets? Because there are advantages. If the available data sets is smaller, we can easily explore. We can easily analyze, we can easily store, okay, and we can easily extract. Whenever we want, we can easily extract. These are the advantages. And also, extraneous, unnecessary number of variables will cause us confusion, complexity. So we can eradicate those problems with the help of dimensional reduction. Okay. Now, let us look into the mathematical perspective of PCA. Before going to the PCA, we must understand what is population covariance matrix of a data set. So let us take a quick look into the difference between let us look at a quick look into the difference between covariance and variance. Okay, see, variance you can understand it as if a data set contains points like x1, x2, x3, x4, okay, and so on, xn. There are so many variables, n features. Okay, n features are there. Seeing x1, x2, x3, so on, xn. Now let us treat let us calculate the average of all these data sets. Say it as x4. Now let us consider the differences between the values and the mean, that is x bar minus x1, x bar minus x2, x bar minus x3, x bar minus x4, x bar minus x5, so on, x bar minus x. That means we are calculating the deviations of the values from the mean. Okay, x bar minus x1, x bar minus x2, x bar minus x3, so on, x bar minus x3. Now, in order to make them positive, let us square them. That means we are squaring. That means x bar minus xi whole square. And we are adding all these squared deviations. That is, we are adding all these squared deviations. Now, we are dividing entire sum with n. Then we get an average. That is called variance. That is called variance of this data set variable capital X, which is where x is nothing but the column vector x1, x2, so on, xn. So variance is nothing but is also a mean of sum of squares of deviations of the set values from its mean. X bar is average, sum of all observations by number of observations. Then what is the variance? It is also a kind of average, which is the average of sum of squares of deviations of the values from the mean. That is called variance. Similarly, covariance represents, suppose there are two column vectors x and y, then covariance will be calculated with the help of mathematical formula, which gives us the amount of variation caused by x in y as well as caused by y in x, mutually, vice versa. Mutual variations caused by x on y and y on x. That is covariance, which is calculated with the help of the formula, C is equal to 1 by n minus 1. You can see covariance formula 1 by n minus 1 summation xi minus x bar whole transpose, where we are calculating the covariance for a set of variables x with the transpose x transpose. So this is the covariance formula which we use to calculate the covariance between two variables. Okay, and let us move to another slide. So covariance matrix, how we write the covariance matrix. With the covariance matrix, we can calculate the entries of covariance matrix, and which is a square matrix given by Cij is equal to sigma of xi comma xj, where the c's are belongs to real numbers d by d, and d by d describes the dimension of a number of random variables of the data, the number of features like height, width, weight, etc. Also, the covariance matrix is symmetric, that is sigma xi comma xj is equal to sigma xj comma x. Let us look into the meaning of these things. See, first, covariance matrix is denoted by C, which is nothing but a matrix Cij with an order d by d. Okay, and each Cij will be either variance or covariance. Either variance or covariance. If it is variance, suppose that is C11, C12, so on C1n, C21, C22, so on C21. In the similar way, Cn1, Cn2, so on Cn. Okay, here C11 is nothing but the variance of x1 with respect to itself. C22 is the variance of the column vector x2 with respect to itself. CNN is also variance. But C12 is the covariance of x1 and x2. Similarly, C21 is the covariance of x2 with respect to x1. But these two will be equal. Just now we have written here. These two will be equal because C12 and C21 both results into same answer. Similarly, C23 means the variance, the covariance between x2 and x3 vectors. The covariance between x2 and x3 vectors. Okay, and in this way we can calculate the covariance matrix Cij with the order d by d, where d is the number of variables features we want to contain in our data set. Okay, actually the covariance will be calculated with the help of this formula between two vectors. The covariance will be calculated. Suppose we have two vectors x comma y, then the covariance of x comma y, where x is a column vector x1, x2, so on xn, and y is a column vector y1, y2, and so on yn. Okay, then covariance is calculated with the help of the formula xi minus x bar into yi minus y bar by n, because n is the number of observations in each column vector. This is the original formula of covariance. Now, with the help of variance and covariance, we'll construct the covariance matrix for the given data set. Okay, and now let us see how we are going to, with an example, we'll try to understand how we are going to build a covariance matrix for a given set of data. So, this is a data set. Suppose X represents a data set, and the first feature is x1, say heights of students of IARE, and second feature is x2, the weights of students of IARE. So on, there are p features like IQ of IARE students, or their skills in particular sport, that is x3, their skills in cricket x4, their skills in football, like that. We have taken so many. We have taken a matrix. The first vector represents the heights, second vector represents the weights, third vector represents their ability in programming or coding x3, the fourth vector represents their IQ in mathematics, the fifth vector represents their IQ in their core engineering. Like that, we have a set of p vectors, p features. Okay, they are represented in a matrix. Okay, now this is our data matrix n by p. It is of order n by p. Now, see, this is our covariance matrix between a variable xi with respect to itself. Okay, covariance formula. Now, let us take a practical example with a three variable data set, which is represented by the first variable height is denoted by x, and the second variable y denotes test score, and the third variable represents the age of 5 students. We are considering the data about 5 students, say student A, B, C, D, E. The first vector capital X represents the heights of 5 students, and in inches, and the second column represents the test score. That means we have conducted some cognizant has been conducted a test, some IQ test. In these scores, 5 scores, the student A scored 580 marks for 700. Of course, the score may have been conducted for 700. The first student score is 580, and the second student score is 570, third is 590, fourth one 660, fifth one 600 out of 700. These are the IQ test scores. And third is their age 29 years, 33 years, 37 years, 46 years, 55 years. Now we are going to construct a covariance matrix for these three vectors x, y, z. Okay, so let's look into those details. Before going to the calculation of variances and covariances, we need to calculate x bar, y bar, and z bar. That is, average height. We need to calculate average height of 5 students and average test score of 5 students and average age of first 5 students. If we calculate the average, that is x bar, and the average of scores y bar, and the average ages z bar, the values will be, see, the average, if you calculate the total sum of all observations by 5, you will get some 68. And if you calculate all these things and divide by 5, you will get some 600. And if you calculate all these ages and divide by 5, you will get 40 years. So the average height of these 5 students is 68 inches, and the average IQ of these students out of 700 marks is 600, and the average age of these 5 members is 40 years. This is what we found. Okay, now we are going to calculate the variance of x, and I'll tell you how to calculate the covariance between x and y. The small example. So see here, first variance will be calculated like this. Variance means sigma x square. You can write sigma x square, which will be calculated with the help of the formula. 64 minus mean 68 whole square plus 66 minus 68 whole square plus 69 minus 68 whole square plus 68 minus 68 whole square plus 73 minus 68 whole square. That means we are taking the deviations from the values to its mean. 64 minus 68, 66 minus 68, 68 minus 68, 69 minus 68, 73 minus 68. In that way, we have calculated the deviations and we have squared them, and we are dividing. Total there are 5 brackets, 1, 2, 3, 4, 5. So we are dividing them with 5. Then we get an answer, that is the variance of the feature x, the variable x, the variance. Of course, that will be listed in the next slide. Now, I'm going to calculate the covariance. In the same way, you can calculate sigma y square and sigma z square. In the same process, you can calculate the covariance, the variance of x, variance of y, and a variance of z. Same process. Now, I'm going to tell you how to calculate the covariance between x and y. Covariance between x and y. See, to calculate the covariance, we need to write what is, see, I'm writing here x bar. X bar is 68, the average height, and y bar is 600, the average IQ score. And we'll calculate the covariance between x and y. Covariance between x and y, it is also denoted as sigma x comma y. With the help of the formula, 64 minus 68 into 580 minus 600 plus 66 minus 68 into 570 minus 600 plus 68 minus 68 into 590 minus 600 plus 69 into 68 into 660 minus 600, 73 minus 68 plus 600 minus 600. In this way, we'll calculate the product. That means we subtract 64 minus 68, 580 minus 600, and we multiply both of them. We subtract 66 minus 68, 570 minus 600, and we are multiplying both of them. And we take the deviation of 68 minus 68, 590 minus 600, and we are multiplying. 69 minus 68, 660 minus 600, we are multiplying. 73 minus 68, 600 minus 600, we are multiplying. Like this, we'll add 5 products. We'll add the 5 byproducts, and we get the covariance sigma of x comma y. This is the covariance of sigma. Similarly, we can find the covariance of sigma x comma z and sigma y comma z in the same process. Then, with the help of these calculations, we are going to get a 3 by 3 matrix, which is called covariance matrix. Let us look at that matrix. So finally, we got, this is the covariance matrix. This is the variance of x. This is the covariance of x and y. This is the covariance of x and z. This is the covariance of y with respect to x. And this is the covariance, this is the variance of y. This is the covariance of y and z. This is the covariance of z and x. This is the covariance of z with respect to y. And this is the covariance of z. If you keenly observe, you see that these two are equal and these two are equal and these two are equal. That means we observe that the covariance of x and y is as same as the covariance of y and x. Similarly, the covariance of z comma y is as same as covariance of y comma. That means the symmetry exists between the covariances. That is why the covariance matrix is always symmetric matrix. The covariance matrix is all. That means if you transpose this C, you will get C itself. C transpose is equal to C. That is why this covariance matrix will always be a symmetric matrix. Now we'll go to some eigenvalues. We'll obtain the eigenvalues and eigenvectors for this matrix, and we'll do some mathematics called singular value decomposition or pure decomposition. And those decompositions help us to decrease the dimension of the given data set, the heights, test scores, and the age. Okay. So let us look into the geometrical interpretations of PCA, principal component analysis. We are considering a two-dimensional data here. That means we have a two-dimensional data set, okay, which is represented by x1 and x2, centimeters and inches. We can project it into one dimension. Then the data will be compressed. That is called dimensionality reduction, data compression. Okay, I am going to explain the visualization of this dimension, reduction of two dimension into one dimension in the next slide. Yes. You see this? If you project this point onto, this is a plane. If you see, this is a plane, xy plane. Okay, so that means two dimensional. This is two dimensional because we are on x1, x2, that is xy plane, we can say, or x1, x2. Now we are taking the perpendiculars. That means we are projecting the points perpendicularly onto the floor. Okay, onto perpendicularly. That means this will be projected to this point. This point will be projected perpendicularly. The perpendicular projection, the perpendicular, the perpendicular, the perpendicular, the perpendicular, and the perpendicular. That means these points which are flowing like this in the two-dimensional plane, when you project them into a straight line, one-dimensional, they will be in a linear form. They will all follow a linear form. That means you have projected with the perpendicular projections, you have projected two-dimensional data into a straight line called one-dimensional reduction. That means, like when we have some kites flowing in the when there are some stars sticked on a wall, and you have just pulled them onto the floor. All those stars, when you pull them perpendicular onto the floor, they will form a straight line. That is called reduction of two-dimensional data into one dimension. Okay, now let us go to three dimension. See here, data comparison of three dimension into two dimension. We are having three, like our test scores, age, and heights. This is a three-dimensional data: x1, x2, x3. That means we are in space. We are in a room, and we are seeing some points plotted in this room. That is called this picture. And if you rotate the angle, you can view the spread of the data in any angle which are you are convenient with. You can view like this, you can view like this, you can view like this. When you rotate the cube into this, the data is like this. Okay, now you are projecting each point onto a floor, onto the perpendicular floor. That means you are projecting the points which are spread in this room with a perpendicular straight to the ground. Then you will see this projection. then you will see this bridge. When you project every point onto the ground, onto the perpendicular ground straightly, you will get this bridge. That means this three-dimensional data is being reduced to a two-dimensional data. This is also called data compression or dimensionality reduction. So let us look into some applications, image processing or image compression with the help of PCA or dimensional reduction. Here you are seeing a 100 by 100 image. That means you can see when you suppose you have 100 by 100 pixel image, 100 by 100 pixel image, it occupies 10,000 dimensions. It occupies 10,000 dimensions of storage space. That means it is occupying a huge storage space. So you want to reduce it without disturbing the clarity of the picture. You want to reduce. So what you will do? So with the help of principal component analysis, okay, like 3-dimensional, 2-dimensional, you can project a 100 by 100 dimension into a less dimensional space. Okay, with the help of PCA. So for your better understanding, here we are considering a 12 by 12 pixel data, which is a 144 dimension, because 12 into 12 is 144. It occupies 144 dimensions in your data storage. So you want to reduce it without disturbing the clarity. Okay. So it is a picture about a butterfly and some flowers. Now you have reduced by using this PCA and dimensional reduction. You can reduce it into 144 dimension into 60 dimensions. That means root 60 into root 60. Then you see the same picture, but the clarity is little missing, but you have preserved at most 95% of the clarity. By reducing 144 dimensions to 60 dimensions, you preserved at least 90% of the clarity of the picture. But if you reduce the dimension to further, like this example 16D, you are missing the clarity. Some vision clarity vision is missing. If you decrease the further, like 144 into 6 dimensions, it is more clumsy. So 6 dimensions is not preferable. And even the 16 dimension is also not preferable because the picture is not clear. But 60 dimension, we are having the same clarity as 144 dimensions. Of course, there is a little compromise of accuracy, I agree, but it is very less, like 5% or 2%. Okay, but the thing I want to tell you is when you reduce this 144 dimensions into 16 dimensions, that is this picture, you'll decompose all those 16 dimension matrix into 16 vectors. Okay, these are the 16 most important eigenvectors. Okay, these 16 more eigenvectors plays a very important role in reducing the dimension. In the similar way, when you reduce to 6 dimensions, you will get 6 eigenvectors working background in the reduction of dimensions. Okay, this is finally one dimension which is completely clumsy. So this gives you a more clarity on, this is the one dimension. So this gives you more clarity about the data compression and a dimensionality reduction. Okay, in the image process. So with this, I'd like to conclude the principal component analysis with a small summary. This is nothing but projection method to reduce the number of variables and to transfer a set of correlated values into new set of uncorrelated values, mapping the data into a space of lower dimensionality, and it is a form of unsupervised learning. These are the properties of principal component. The features of principal component analysis, and the properties, it can be viewed as a rotation of existing axis to new positions. You can view it any position, and new axes are orthogonal to represent the directions with maximum variability. The axes of principal components are always perpendicular to each other, okay, in any dimension. So with this, I'd like to conclude the lecture, and we will meet with the next concept in the next class. Thank you all for your patience. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.